Hello. So the next thing we want to talk about is section 11.3. It's Taylor series. So this is kind of like a mixture of the last two sections. So we kind of had Taylor polynomials, were these sort of finite polynomials that estimate a function. And then power series are these infinite polynomials that sort of converge at different values of x and so on. And so what we want to do is merge those two and figure out, okay, so take those Taylor polynomials, let those run to infinity, and then sort of go from there. All right, so to form a Taylor series, what you're going to do is you're going to have a function that's differentiable on an open interval centered at a point x equals a. And the derivative has to exist for all orders. So like the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, all have to exist. So you might sort of think about this. This is fairly common to occur, but then again, like things like tangent, tangent's not differentiable at pi over 2. So you can't sort of have a Taylor series that includes the interval that has pi over 2 in it. So you got to be kind of careful about what point you choose as your center of that Taylor series. So the Taylor series is going to be defined as sort of the function evaluated at a, the derivative at a times x minus a, the second derivative at a over 2 factorial times x minus a squared, and so on. And so what this is going to do for us is this function, which is an infinite series, will match the function f of x for all of its derivatives at x equals a. Okay, and so this is sort of a series centered at a. It's going to work out nicely for this. And I'm missing, I guess, in here, there should be an x minus 3 or x minus a to the third here as well, right? So the x minus a term comes in each of them with a power in it. Okay. So the k here is the derivative, the kth derivative of the function f. K is a kth derivative at a divided by k factorial times x minus a to the k power. Okay. The reasoning is exactly the same as what we had before. If I take a derivative, it sort of pulls a 2 in front, a 3 in front, or whatever. The exponent comes in front, then the exponent comes in front, the exponent comes in front. So you sort of get this factorial thing that you have to cancel out in the denominator, which is what's down here. That works out. If I center a Taylor series at 0, this is called the Maclaurin series. So we just, terminology wise, that's just called the Maclaurin series. Taylor series, Maclaurin series. They might ask for a Taylor series centered at 0, even when they mean a Maclaurin series. They will not ask for a Maclaurin series when they want like a Taylor series centered at a different point, at x equals 1 or something like that. They'll always ask for a Taylor series in that situation. The Maclaurin series just takes away the having to say at x equals 0, centered at x equals 0. Okay. So in order for them to be kind of useful, we need two things. Well, first thing is like, where is its convergent? Does it converge for values of x, all values of x, some of the values of x, small values of x, values of x between -1 and 1? What does it do? So this is sort of the power series thing that we had before. Where does it converge? The second question is really the one we actually need to sort of, we don't do a lot of work on, but it's a question that's really important, is where is it actually going to be equal to the function value? So is it true that where that sort of converges is exactly where the Taylor series is equal to the function value? And so that's kind of a little bit of a trickier question. We're gonna skirt that a little bit and mostly talk about where it's convergent again, because that's what we did in our power series as well. Okay. So we can find this. It's not too hard to do. So the Maclaurin series for the function cosine of x, meaning Taylor series centered at 0 for cosine of x. Find the first derivative at 0, second derivative at 0, third derivative at 0, fourth derivative at 0, and so on, right? And so what do I get here? Well, the first derivative of cosine is sine, negative sine of x. Oh, but I plug in 0, so this is f prime of 0. And sine of 0 is 0. So the second derivative at 0 is negative cosine of 0, which is -1. The third derivative at 0 is sine of 0, which is 0. The fourth derivative at 0 is just cosine of 0, which is just 1. And that's where it sort of repeats, right? So the original function is cosine of 0 is 1. That's my f of 0. Okay. Now I want to form that Maclaurin series from this. So using that information, what am I going to see? I see that every other term is 0. So that's sort of every other term is this sign. So it's 0. Those are the odd powers of x. Only the even powers of x have a coefficient, and it alternates in sign. So it's +1 for the first term, this -1x squared in the second term over 2, and then 1x to the fourth over 4 factorial in the third one. And so then I kind of go from there. All right. So I form that. I've got 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth. And then it's going to continue with that pattern. So it's going to be 1 minus 1 over 6 factorial x to the sixth, and so on. So now I have to go in and sort of figure out a way to write this in a summation form. So the general term here has an even power of x. And to write an even power, I take 2 times any number and I get an even number, divided by that same thing with a factorial on it. And that goes from 0 to infinity. And then I actually have a -1 to the k here as well, because that's an alternating series. It's an alternating series. All right, so that means we end up with cosine of x is -1 to the k over 2k factorial x to the 2k. All right, then we need to ask, where does this converge? So where does it going to converge? Well, now I go through what I did the last section, right? I find it using the ratio test, right? So I take the limit as k goes to infinity of -1 to the k plus 1 over 2k plus 1 factorial x to the 2 k plus 1 divided by -1 to the k x to the 2k over 2k factorial. Okay, and the absolute value just kind of takes care of that -1, so we're sort of done with that. And what I'm left with is just going to be x to the 2k plus 1, 2k plus 2 factorial, and then I have 2k factorial, and then x to the, oh, it's really 2k plus 2 on the top of that exponent, right? X to the 2k. So I get x to the 2k plus 2, 2k factorial, 2k plus 2 factorial, and x to the 2k in the bottom. All right, what do I end up with there? So the x to the 2k and the 2k cancel, so I get x squared. 2k factorial is 2k plus 2 times 2k plus 1 times 2k factorial. So I actually have a 2k factorial on the top and the bottom. And I'm left with a 2k plus 2 and a 2k plus 1 in the denominator there. So overall, what I get is the limit as k goes to infinity of x to the 2 divided by 2k plus 2 times 2k plus 1. Now, for every x I plug in, that's a finite number. So the top is fixed. The bottom is going to infinity. So this whole thing is just 0. What does that mean for our radius of convergence? It means no matter what I plug in for x, I get convergence. So here, x is everything. And so the way my math lab will do this is a little bit funky, but they'll put a -infinity less than x less than infinity, which is just, in my mind, just sort of insulting. But you do the same thing for interval notation, but that's what they're going to maybe want in their answer. So there you go. All right, cool. So let's try another one. We're going to try Maclaurin series for 1 over 1 minus x. We do actually have this series already. This series we found as the geometric series. And so it's a geometric series where x is less than 1. So the same convergence is going to kind of go on here. But I can do this. So the first is just going to be 1. The second is just going to be 1, which is 1 factorial. The second derivative is just going to be 2, which is 2 factorial. The third derivative is just 6, which is 3 factorial. The next one will be 24, which is 4 factorial, and then so on. And so what we end up with here is the top and the bottom of this. is going to just give me k factorial over k factorial. So the Maclaurin series of 1 over 1 minus x is just the sum from 0 to infinity of x to the k. And so that's great. The really nice thing then is that actually we've done this before. We actually get the geometric series, and that geometric series is convergent from -1 to 1, not convergent at either -1 or +1. So it's not convergent at any of those, just between the two. Okay, so there's a couple things to maybe emphasize here. The first thing is there's actually only one power series representation for any given function about a given point. So the fact that doing the Maclaurin series for 1 over 1 minus x gives me the same thing as what I get from like the geometric series version of finding that Maclaurin series. That is it's on purpose, right? Like there's no way I could have gotten anything else. So there's only one power series representation for any given function about a given point. There's certainly more than one way to arrive at that series. So for this one, we did this by the Maclaurin series, or we did it by looking at the geometric series. We could also look at these things and maybe integrate or differentiate. So for example, something like the natural log of 1 minus x, and maybe I'll do negative natural log of 1 minus x. So to get the power series expansion of this, I could actually just integrate the power series expansion of 1 over 1 minus x, because those two are it's sort of natural log is the integral of that thing. And I could sort of say, oh, we'll just let the constant c be 0 there. That'll be fine. We can get the same thing for both of those. So I can find the Maclaurin series from something other than a sort of Maclaurin series expansion using derivatives. I can do that using integrals. I could possibly do that during derivatives. So taking the derivative of something, maybe I would look at maybe 1 over 1 minus x squared, negative 1 over 1 minus x squared. I could still, again, get that by differentiating all the terms in that Maclaurin series, and that would work out. Okay. So there's a lot of ways to arrive at these things, these series. The second of these is only convergent from -1 to 1. And if I want any convergence anywhere else, I actually have to recenter the series. So I've got to move the center of this thing. So if I want to look at 1 over 1 minus x for x equals 4, well, I actually have to recenter the series. So I'm going to move the series over to where I could actually have a 4 in that interval. And so putting it, maybe centering it at 4 would be the way to go. Or if I wanted at pi, I centered it at 3. And then pi is going to be plugged in, and it will converge for pi because 3, it's within 1 of 3. And that radius of convergence is not going to change. So I just take that whole interval and I just move the interval around without widening it out or shrinking it. So that interval of convergence is always the same. It's just that moving it around left and right. So if I want it at a different point, I need to recenter that series. All right. So I want to think a little bit about the next thing. So the next thing is another way to look at a Maclaurin series, except we're going to use what's called binomial coefficients. So I want to think about these things a little bit. You may or may not have learned how to do this. It's not a thing we sort of always teach, but it's something that sometimes is taught. So when I FOIL out 1 plus x times 1 plus x, so there's a trick to doing this. So I can FOIL it and get what I need. The trick is that if that's bigger than 2, then it's harder. You know, I've got more terms to FOIL out, right? I'm not really foiling in that case. I'm just sort of expanding this thing. So what do? So there's a trick for this. It's comes from Pascal's triangle. So I don't know if you remember Pascal's triangle. I've got sort of 1s on the outside, and then all of the internal terms come from the sum of the previous top 2. As long as there are previously top 2. And then I've got 1s on the outside. I've got 4, 6, 4, 1. These are the coefficients of the terms in 1 plus x squared. And all of the powers of x are in this expansion. So what I get is 1 plus 2x plus 1x squared. So the coefficients 1, 2, 1 from this row occur as coefficients in this expansion. The really nice thing is that this actually works not just for 2, but for 3 and 4 and 5 and 6. I don't want to clear. Let's do this. So for 3, if I look at the next row of Pascal's triangle here, those are the coefficients. So I get 1, 3x squared, x to the third. And notice all of the powers of x are present here. They go from sort of lowest to highest. And that's just because the 1 is in the left of that. And you'll notice these are symmetric. They're the same backwards and forwards. So like if I flip this around, I still get the same coefficients. And so that's how that's going to work. That's great if we have a nice integer here. So what we do here is, this is actually a rule. I use what's called the binomial coefficient. And the binomial coefficient is something you will have learned in a statistics or like a probability class. You're looking at how many ways to choose something out of something. So the binomial coefficient in this case is saying, how many ways can I choose a certain number of x's out of these 3 terms that I'm multiplying? So in particular, how many ways can I choose none of them to be x? There's only one way to do that. I don't choose any of them to be x. How many ways can I choose one of them to be x? Well, either this one is x, that's 1 way, or this one is x, that's 2 ways, or this one is x, that's 3 ways. So there's 3 ways to choose one of these terms to be x. There's also 3 ways to choose 2 of them to be x. So it's sort of the first 2, the first and the third, the second 2. And those are the 3 ways of choosing 2 of them. And then there's 1 way to choose all 3 of them to be x. I just make all 3 of them x. All the rest are just x. All right. So this is where that sort of comes from. We call this thing the binomial coefficient. And in this case, it would be like 3 choose k. That's the way we would write that. Or in general, it's like an n choose p. I can't remember if I do p or I might do r down here, or k, in fact, in some cases. N choose k, we'll just do it that way. So it's the binomial coefficient. It comes from n factorial over n minus k factorial times k factorial. And you don't have to remember this part of it. What I want is I want this factored. So what I do is I factor out the top. I say it's n minus 1, n minus 2, n minus 3, up until n minus k, and then I factor out the n minus k. So what I get is just n minus 1, n minus 2, all the way out till n minus k plus 1. So it's like 1 above the last term that will factor out over k factorial. Okay. And the reason I'm doing it this way, where I don't have factorials for all of them, I sort of have these factorials in the integer case. For integers, this is really nice. This is how it works. It's going to work out this way every time. If I don't have an integer, I can still write the binomial coefficient in this other form. And what's really cool is that will actually give me the binomial expansion of the power series binomial expansion of that exponential function, or that exponent, right? So I can find 1 plus x to the minus 1 by doing this with minus 1, and it's never going to stop. It's going to be minus 1, and then it's going to be positive 2, then it's going to be negative 6, and then so on, right? So I can actually do this with a minus 1 power in there, and that'll actually work out to sort of give me this binomial coefficients for the expansion of this thing into a power series. So this is pretty cool. It's not anything magical. All we're really doing here is we're just shortcutting. So this is just a shortcut for finding the power series of 1 plus x to the power p, any number up there. You can do the power series expansion, the Taylor series expansion, the Courant series expansion, but this is a shortcut to do it. So you don't have to go through all of that work of finding all the derivatives, plugging in 0, doing all the stuff. You can actually just do this power series, this sort of binomial expansion of the thing, and it'll work out. So the power series expansion of 1 plus x to the p is just the p choose k times x to the k. So that p choose k, where we define p choose k with a product on the top instead of a factorial on the top and a k factorial on the bottom. This will converge for x less than 1, absolute value of x less than 1. This is really cool. This actually works out for any power I could possibly put in there. I could put in pi, I could put in 0.5, I could put in -1, and this will be the power series expansion of those functions. Okay, so for example, this is sort of the easy side of things. 1 plus x to the 6th. For 6, I plug 6 in, I get 0, 1, 2, 3, 4, 5, and 6. And then 6 choose 7, if I do this sort of 6 choose 7 calculation, is not actually going to give me anything. It's just going to be 0. I'll get a 6 minus 6 in my product, and 6 minus 6 is 0. And so that will actually just zero out all the terms beyond x to the 6th. So I could sort of think of this as an infinite series with zeros past x to the 6th, and that's fine. That's how it works. And I do get 1, 6, x, 15x squared, 20x to the 3rd, 15x to the 4th, 6x to the 5th, positive 1x to the 6th. All right, one more example. So I'm going to do 1 plus x to the -1. I have -1 choose 0, -1 choose 1, -1 choose 2, -1 choose 3, and then it's going to go on forever because I never actually subtract -1 when I do this. I sort of keep getting numbers out of this, and so that's going to give me my expression. By the way, the choose 0 is always just 1. So -1 choose 0 is 1. -1 choose 1, I guess I do that on here, is just -1 over 1 factorial times x. Then I have -1 times -1 minus 1 over 2 factorial times x squared, -1, -1 minus 1, -1 minus 2 over 3 factorial x cubed, and so on. So this is just actually going to give me an alternating version of 1 over 1 minus x. Again, I can do this. I can plug in minus x into 1 over 1 minus x, and that binomial expansion, I get the same thing. This is another way to do it. So you use this binomial coefficient to sort of get the coefficients of just 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1. The numerator here always, in this case, ends up being the factorial with either a plus or a minus, depending on which sort of parity it is. Is it even or is it odd? If it's even, then it's going to be 1. If it's odd, it's going to be -1. Okay. Other examples. I can do 1 plus x, square root of 1 plus x is just 1 plus x to the 1/2 power. I do 1/2 choose 0, 1/2 choose 1, 1/2 choose 2, 1/2 choose 3, 1/2 choose 4. I get 1 is 1/2 choose 0, 1/2 over 1 factorial, 1/2 times 1/2 minus 1 over 2 factorial, 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial, and so on. This expansion is just going to give me 1/2 x minus 1/8 x squared plus 3/48 x cubed, and so on. And so I can do that. All right. So this is really nice. It gives me a nice expansion of these things. Then I also know that this is going to converge for x between -1 and 1. Sort of nice to know that. And then I also have this sort of nice property of getting the next term is not hard. It's just another idea of this binomial coefficient. All right. So this is the same as the Maclaurin series. It's actually giving you the derivatives at 0. All those terms are just coming from derivatives at 0. I don't have to do the derivatives because I kind of know I can just do this binomial coefficient. And you'll notice when I do the derivatives, like the derivative 1/2 is going to put a 1/2 in front. That's going to be that first term here. And then I'll have like a 1/2 times 1/2 minus 1, because that's the derivative of 1/2 minus 1, right? And then I have a 1/2 is minus 1, 1/2 minus 2, 1/2, 1/2, and so on. So this is actually just giving me derivative of this thing at 0. So when I plug 0 in for x here, I just get 1 to whatever power is just 1. So I don't have to worry about the power term in here. All right. Finally, we want to talk a little bit about error again. So the error here is given by like the next derivative and then evaluated at a point, and then n minus 1 factorial on the bottom, x minus a to the n plus 1 in there. And then I have some value of c between a and x. Well, so what's really nice here is if I say, I know something about the derivatives. So if all of the derivatives are things like sine and cosine, the derivative is not going to be any bigger than 1. So I can sort of bound that thing above by 1 and say, hey, you know, that derivative at c, whatever it is no bigger than 1. then this remainder will be less than or equal to sort of 1 over n plus 1 factorial x minus a to the n plus 1. And so I know how close I'm going to be in that situation. What does that give us? That actually gives us something really nice. It tells me that this converges on the interval if and only if the remainder goes to 0. So I don't have to worry about thinking whether sort of this thing converges by some other convergence test. If I can bind that remainder, I can say, hey, you know, that this thing, as long as the remainder goes to 0, the whole thing will actually converge on that interval. Cool. All right. So with that, we're going to do a lot of practice in here with finding the Maclaurin series or the Taylor series of these things. And then we're going to talk about sort of convergence. Where does it converge? Intervals of convergence, all that kind of stuff. And then I think there's a very small little bit at the end of this with the Taylor series interval remainder stuff. So the remainder stuff, you're basically just looking at it and saying, can I find an upper bound on that remainder so that it can show that it will actually go to 0. And then if I can show it goes to 0, then we're happy to sort of do that. Okay, cool. Nice. So next time we'll talk about other ways to use these Taylor series. So things like maybe I can differentiate them, integrate them, all that fun stuff. But in fact, I can do all of those from the power series section. But then we say, well, what's the use? So what's the point of doing all of these things? Is there a way that I can make it easy? All right. We'll talk next time.